let's look at this, see if we can make sense out of it. It's not crucial that you do make sense out of it, but hopefully this kind of gives you the idea of what we're looking at. Imagine we have a function, f of x equals 2x plus 10. That's our starting point. F of x equals 2x plus 10. And the function big F of x is intended to be an antiderivative for that function. Let's look at this. If we have a continuous function on an interval I, I'm going to do a linear function. We know linear functions are continuous. A continuous function on an interval I, then it has, if you pick an A in the domain of that function, then it has an antiderivative on that interval, and the antiderivative is given by this. Basically, if you integrate from A to x and let x be the independent variable of the function f of t dt, this qualifies as the antiderivative. I should probably show this really quickly, and I will. But let's just see what the function is. What if we start with this linear function, and you see the graph right there, there's the graph, f of x equals 2x plus 10. It's an increasing function on the interval. What is the antiderivative function that I'm defining? Well, big F of x is the integral from, and it's pick the number 0 to x of 2t plus 10. Basically, we replace the x with the letter t and integrate with respect to t. And the function just tells us what's the area under the curve between 0 and this number b right here that's changing. So you see the area from 0 to 3 evidently is 39. And as we scoot over a little bit, the area from 0 to 4 is 56. So this antiderivative function is the function that tells us what's the area, and I guess it technically is the net signed area. The net signed area between the curve and the x-axis on the interval from 0, and the 0 is arbitrary, it can be anywhere in the domain of this function, but from 0 to x. So it's really kind of a, if you want to think of it as an area function or net signed area function, that's what's going on there. Let me scoot this over so we can see a little bit more of what's going on the screen. So it's the net signed area function, and just look, suppose we're calling this big F of x, we're calling this the antiderivative, or an, there are lots of antiderivatives for a given function, but an antiderivative. So what if we take the derivative? Now to take the derivative of this function, what I did was use, back up here, what I did was use the fundamental theorem of calculus part 1, where it said we can find an antiderivative of the function in here, evaluate at the upper limit and at the lower limit. So the derivative of this function is the derivative of what we get. So the 2t, that would be I've left out a step. Basically, what I should have shown a little bit more of was that I found an antiderivative t squared plus 10t. And then I substituted the x for the t, and I substituted the 0 for the t, and then subtracted. That gave me x squared plus 10x, and then I took the derivative of that to get 2x plus 10. I don't think I want to push this picture that much farther, except when we talk about this f of x equals the integral from 0 to x, it's the function that tells us the area of the shaded region, in this case there. All right, back to the notes there. Maybe what I could do is just take this and imagine that we can just look at example 9. I want to find big F prime of x two different ways. So big F of x equals the integral from a to x of sine t dt. what is the derivative of this function? Basically, what is d dx of the integral from a to x sine t dt? Fundamental theorem of calculus, part 2, would simply have us say it's equal to sine x. But let's show that. So what I want to do is find the value of this and then take the derivative. So I need an antiderivative for sine t. What can you take the derivative of and get sine t? Negative cosine t. So this is going to be d dx of negative cosine t, evaluating this at the endpoints from a to x. And recall how we do this. We take the x and substitute it in. We take the a and substitute it in. And then we subtract. So this is going to be d dx of negative cosine x minus negative cosine a. So this is going to be d dx of negative cosine x plus cosine a. Now the number a can be any number in the domain of this function, so basically it can be any real number. So the cosine of a is simply a constant. A is a constant, so the cosine of a is a constant. The derivative of a constant is 0. So if I take the derivative of negative cosine x, I get sine x. If I take the derivative of cosine a, I get 0. So this equals sine x. So effectively, when we're taking the derivative of this function defined using this definite integral with the independent variable at the upper limit, effectively that x just gets substituted for the independent variable that's used in the integrand, and it's just that expression, sine x.
Well, how do we know that x isn't just a normal variable like a?
The way the function's defined, f of x,
Oh, okay.
f of x equals the integral from a to x. So for different values of x, you could put in pi for x or 2 pi, whatever. The value of this integral will be different. Yeah. Okay, and the b part wants us to apply the fundamental theorem of calculus and reach the same conclusion. If we have f of x equals the integral from a to x of sine t dt, then big F prime of x equals d dx of the integral from a to x sine t dt, and that's sine x. And just a restatement, I guess I could copy it and paste it, or write it down. A restatement of the theorem that we're applying is this. d dx of the integral of little f of t dt is what we get when we evaluate that function at that variable limit of integration there, up there. 10, sorry. Closing out the section, these first couple examples do not require much work. The second one, the third one, I don't think requires much more. I think we'll have to take a derivative to get that one. Just evaluating this function at 0, f of 0 is equal to the integral of the square root of cosine t dt from 0 to 0. So that's going to be 0, yeah. From 1 to 1, from 2 to 2, from pi to pi. If the lower and upper limits of integration are the same, then the value of the integral is 0. So f of 0 is 0, just like that. Now, for f prime of 0, I really need an expression for f prime of t. So write an expression for f of t, sorry, not f prime of t, f prime of x. So let's find f prime of x. F of x is the integral from 0 to x square root of cosine t dt, just copying and pasting there. F prime of x equals d dx of the integral from 0 to x square root of cosine t dt. And applying the fundamental theorem of calculus, what do we need? We need the fact that square root of cosine t is continuous. Cosine t is continuous everywhere, and it would be continuous at least from the right at 0. Probably wouldn't want to go to the left of 0. And I suppose we could have concerns about cosine t actually being negative. That could potentially be a concern, except that in the first quadrant, at least between t equals 0 and t equals pi over 2, cosine is going to be positive. Cosine is positive in the first quadrant. So I believe we're okay there. So the derivative is going to be, well, what? Big F prime of x equals the square root of cosine x. So big F prime of 0 is going to be the square root of the cosine of 0, which is the square root of 1, which is 1. So it does require us to use the fundamental theorem of calculus, part 2, to come up with an expression with an x in it, the derivative. And having done that, we can evaluate the derivative at 0. And we get 1 in this case. For f double prime of x, we've already applied the fundamental theorem of calculus, part 2. And so we just take the derivative that we found. If we know that big F prime of x equals cosine x to the 1/2 power from part B, we just use the chain rule and find the derivative of that. So, generalized power rule, 1/2 cosine x to the negative 1/2 times the derivative of cosine x, which would be negative sine x, there, sine x. And so f double prime of x equals, I want to say negative sine x over 2 times the square root of cosine x. And then evaluate this at 0. And I think it's well defined, and equal to 0. Negative sine of 0 over 2 times the square root of cosine 0. That's going to be negative 0 over 2 times the square root of 1. That's 0. What if I change this to cosine x? Mess up my domain. I think it's going to be in radians. Cosine x. It would look like that. And at 0, if I increase the x value by 0.1, increases the area by 1.01. There we go. Okay, so that's well, actually no, I should go with the square root of cosine x sqrt. That's curious. Interesting domain for that function. So it's only going to give us values in the first quadrant and the fourth quadrant where the cosine function is positive. And then it leaves us in the dark in the, see there's the first quadrant here, then there's the second quadrant and the third quadrant where cosine is negative. And then once we get to the fourth quadrant right there, then cosine would be positive, and then it wraps around back to the first quadrant again. So, so there we go. So the function that we're looking at looks like that. Okay, that might have been worth doing. Let's look at 5.5. So somewhere, we'll see to the notes, I asked the question. We just use the chain rule to find the derivative. We remember the chain rule. What it says to do if we are differentiating the composition, let's say big F of g of x, then all we need to know is an expression for the derivative of big F and the derivative of little g, and we can express the derivative of that composition in terms of them. Basically, big F prime of g of x, it would be great if that's all there was to it, but the chain rule, of course, says we have to multiply by the derivative of what's inside the parentheses. So we multiply by g prime of x. So we've been there, we've done that, we've applied the chain rule to countless functions to this point to find the derivative. Integration by substitution is a fairly widely used technique for integration. It's going to continue to be used in Calc 2. A good portion of the second chapter, if not the first chapter, that's done in Calc 2 will be integration techniques. And integration by substitution will be a big deal. And you want to get as comfortable as you can now, and you'll get more comfortable in Calc 2. But basically, integration by substitution requires one to set up the integrand and make it look like the answer that you would get after differentiating using the chain rule. Basically, we want to make the integrand look like that. See, there's the integrand there. If we can make it look like that, and we can identify what big F is, and we can identify what little g is, then we know, according to the chain rule, that an antiderivative of that would be big F of little g of x. So when applying integration by substitution, here's the situation we need. We need a function that could be written as the composition of two functions where the derivative of the inside function appears as a factor elsewhere in the integrand. So we need to look at it and say, oh yeah, I recognize that as the composition of two functions. And that inside function, look at that. The derivative of that inside function is right over there. Now, usually what we'll have to do is finagle the integrand, use a little bit of creativity and cleverness to make it look like what we need to make it look like. But if we can, then we can use this technique of integration by substitution to come up with antiderivatives of otherwise horrific looking integrands. Now, it doesn't have to be in the form big F prime. It can just be some function little f, just so long as eventually we can figure out what is an antiderivative for little f. If we know the antiderivative for little f after writing in this form, then we'll be able to come up with come up with some integration. So I have some expressions just to kind of get us warmed up to this notion of writing an expression where we have part of it that's the composition of one function with the other. Sine function composed with the 3x squared minus 4. So we got the sine function as the outside function, and we're taking the sine of the polynomial 3x squared minus 4. So 3x squared minus 4 is the inside function. And we're wondering, what's the derivative of 3x squared minus 4? It's 6x. So what we would need is a 6x somewhere attached to this, multiplied by this, and that's what we have. So if we can write the expression, so we've got some function, sine function, whose antiderivative we know, and we know the antiderivative for sine function. It's composed with 3x squared minus 4, and then we've got the derivative of 3x squared minus 4 attached to that as a factor. That's the situation we need. The b part there, the x squared minus 5x quantity to the 5th power. Hopefully this will be no worse.
Looking for better.
Better is better than not worse, I guess.
Yeah.
So we've got an expression that's raised to the 5th power. So I'm thinking we're composing the function that raises things to the 5th power. What's the function that raises expressions to the 5th power? Well, just plain old x to the 5th. That's, if you want to raise something to 5th power, you do that to it. you apply the function f, and that raises it to the 5th power. So it's this function composed with the inside function. What are we raising to the 5th power? X squared minus 5x. So it's the raised to the 5th power function, x to the 5th, composed with the x squared minus 5x function. And then all that's missing is the derivative of the inside function. What's the derivative of x squared minus 5x? Well, I threw in just a little extra factor of 2 here to make things more difficult. Yeah, we were hoping for better, and I went with not much worse instead of better. So what we'd like is 2x minus 5, right? 2x minus 5 would be much better. But it's almost as good to have 4x minus 10, because what we can do is this. We can take the 4x minus 10 and write the expression 2 times f of g of x times g prime of x. Now, where in the world did that come from? Hang on. I'm thinking it, but I need to show where it came from. Because what we have is f of g of x. This is x squared minus 5x to the 5th power. And then here's a 2, and here's a 2x minus 5. So we see the inside function. We see it's raised to the 5th power. We see the derivative of that inside function there, 2x minus 5. And we had to factor out a 2 to get that 2x minus 5.
Okay.
We had to factor out a 2 to get the 2x minus 5. So when we did, I just took the 2, brought it out in front, and then it looks like this. See, in a lot of cases, we may be off by a constant. And when integrating, it's never a problem if we're just off by a constant, that is multiplying by 2, or multiplying by 5, or dividing by 5, because that constant can always be passed through the integral, and we can get that out of our way, and just multiply it by the final answer. So if we're just off by a factor of 2 or a factor of 1/13 or whatever, that's okay. We never worry about that. We just pass it through the integral and deal with the rest of the expression. So that's the reason I allow for a constant there, k times f. Let's see, sine cubed of 2x times the cosine of x. So what's the outside function? I want to say it's the cubing function. It's a little tricky in the case of the sine function. If I had written it like this, sine of 2x and a big set of brackets and then a cubed on the outside, it would be a lot easier to see that sine of 2x is the inside function and the cubing function is the outside function. It would be easier when written like that. The notation means that, but it's not as clear. With this, you can see the sine 2x is the inside function. So g of x is the inside function, the sine of 2x. So it's the x cubed function composed with sine of 2x. What we need is the derivative of sine 2x somewhere else as a factor. What is g prime of x then? G prime of x. Well, the derivative of the sine of something is the cosine of that something times the derivative of that something. Right? The chain rule says we have to multiply by the derivative of 2x. So we multiply by the derivative of 2x and we get 2. So the derivative of sine 2x is 2 cosine 2x. So again, we're off by a factor of 2. And that's okay, because we can write sine of 2x to the third power times cosine, I want to say this, I really need 2 cosine of 2x so this is our f of g of x, and this is our g prime of x, but this is not equal to the original expression. The original expression doesn't have the 2. So what we have to do here is we have to adjust by multiplying by 1/2. What we have here is see in this one up here we had an extra 2 that we didn't need, and here we're missing the 2. If I write this in the form f of g of x times g prime of x, so 1/2 f of g of x times g prime of x would be a way of writing this expression with the f and the g that I've noted here. So with this f and this g, it's equal to 1/2 f of g times g prime of x. Let me make sure this one, with this f and this g, it's equal to 2 times f of g times g prime of x. Yes, so kind of with it has all these parts. I have to name the f, have to name the g, and I have to show that it's equal to that constant times f of g of x times g prime of x. And then the d part, what's the outside function? What's the inside function? It's a little bit easier to see in this case, I think. Outside function, I want to say it's the square root function. Square root function. And the inside function is what we're taking the square root of, x to the 4th minus 16. What is the derivative of x to the 4th minus 16? 4x cubed. So I have a 4 that I don't need. I'm going to take the derivative. so what I can do is this. If I take the original expression and I write it, if I write it 1/4, see, I'm trying to compensate for having that 4 that I don't need. If I write 1/4 times x cubed, no, not the x cubed, sorry. I want to put it in order, f prime of g of x, or f of g of x, square root of x to the 4th minus 16 times 4x cubed. So I want to set up so it looks just like this. I want it to look just like that. So I say my k is the 1/4, and the square root of x to the 4th minus 16 is f of g of x, and the 4x cubed is g prime of x. So with this f and this g, my expression is equal to this. Now look at the next example, we see what good this does. We see what good this does. It actually enables us to find antiderivatives of these functions. So let's see. Let's do this for 1, and then we'll see how we can use this for the ones that show up in example 2, which should be surprisingly similar to the ones we just got to be working with. All right. So in practice, what do? In practice, instead of calling the inside function g, we use a different variable. Instead of giving a different name for the function, instead of saying let g of x be the inside function, we let the variable u be that expression, and then we try to rewrite all the x's in terms of u. So we go from having an integral with x's in it to having an integral with u's in it, but hopefully a much simpler looking integral with u's in it.
This is kind of like what we did in algebra, where we just substituted like un instead of, and did our factoring that way.
Yes, there's a type of problem that we do where there's an equation that's quadratic in form. Mm-hmm. It's kind of rough looking, but we let u be some expression with x's in it, and after the substitution, it's a lot nicer looking. And it's kind of the idea, make it nicer looking by using a different variable. So imagine that we have this expression, the integral of f of g of x times g prime of x dx. This is kind of how it's going to work. After we go to the trouble of writing it, it takes some work to get it to look this nice. But once we get it to look like this, we will let u equal that inside function g of x. Let u equal g of x. Then we'll take the derivative. We'll find du dx. Then du dx equals g prime of x, and we'll write it like that. Then, to make it substitute more cleanly and neatly into the integrand, we'll write this using differential notation. So if I multiply both sides by dx, if I think of it this for the moment as du over dx, like we did when we were talking about differentials, multiply both sides by dx, we have du equals g prime of x times dx. No, not dx. Yes, dx, sorry. Yes, du equals g prime of x dx. So look back up at the integrand and see what this looks like. This is u. U equals g of x. This is du. So if f is a nice enough function where we know an antiderivative for f, this gives us something we can totally integrate. F of u du. And we're just looking at the function f, whose antiderivative we know. And we find an antiderivative of that. Say the antiderivative is big F. This equals big F of u plus c. And then the original integrand had x's in it, not u's. So our final answer needs to have x's in it instead of u's. So we go back and we ask ourselves, what was u? U was equal to g of x. So we put the g of x back in there for u, and it's f of g of x plus c. And then that's our final answer. And all that it requires, as though it's a simple thing, knowing an antiderivative for little f, knowing that big F is an antiderivative for little f, and being able to write the expression as the composition of a function little f with g of x, with g, so that a derivative, the derivative of g, also appears as a factor of that integrand, and maybe that's the hard part. Let's see if we can make this happen for examples 2a and b. We didn't spend a lot of time with example 2a. I just observed that 3x squared minus 4 was the inside function and sine was the outside function. So much of this is done, well, the whole thing is done for us. I'll just talk through it. What we do is we say, okay, this is the inside function, so we let u equal 3x squared minus 4. Now what we need to see is the derivative of 3x minus 4, 3x squared minus 4, somewhere else in that integrand, and we have it, the 6x. Without the 6x, this doesn't work. Now, if we had a number different from 6, we'd be okay. But if we don't have that x, it's a real problem, and we won't be able to do this. The fact that there is an x there makes this work. Take the derivative of 3x squared minus 4. Du dx equals 6x, and then multiply both sides by dx. And we have du equals 6x dx. Then we look. We actually don't. 3x squared minus 4 is the u. So we put that in there. And 6x dx is du. So we put that right there. And that gives us this integral. And the problem actually isn't complete. I feel like I should go ahead and finish this. What's an integral for, an antiderivative for sine of u? Negative cosine of u. So tack on a constant integration for that, plus c. And then the u was 3x squared minus 4. So it's going to be negative cosine of 3x squared minus 4 plus c. And then the fun part, check the answer. Don't have to, but sometimes it's satisfying after going into all this challenge, because usually checking is not too tough. Derivative of negative cosine of 3x squared minus 4. Sine of 3x squared minus 4, and then the chain rule says multiply by the 6x. And then once we do that, we think, oh yeah. Yeah, we just kind of undid the chain rule. So the process of reversing the chain rule takes some work, but that's kind of what we did. Basically reversed it. All right, over here, let u equal the inside function. What's the inside function? X squared minus 5x. Now we know the derivative of that is 2x minus 5. We don't see a 2x minus 5. But really the next best thing, so when we have du equals 2x minus 5 dx, we're going to be able to rewrite that integrand So there's going to be a 2x minus 5 dx. Because we need to be able to pick up that 2x minus 5 dx and put a du in its place. And that's not going to be a problem. What we have here is the integral of x squared minus 5x to the 5th power times 2 times, times 2x minus 5 dx. So look inside that integrand and everything looks good. X squared minus 5x, I can pick that up and replace it with a letter u. The 2x minus 5 quantity times dx, I can pick that up and replace it with du. The only issue is the 2. So the 2, I can just drag that out in front of the integral. I can say this is 2 times the integral of x squared minus 5x to the 5th power times 2x minus 5 dx. Having done that, all the x's can be replaced by u's. It's going to be 2 times the integral of u to the 5th du. Not the final answer, but it's kind of a satisfying place to stop and take a breath, because we know we can get there from here. Antiderivative for u to the 5th. U to the 6th over 6 plus c. It's just a matter of what I want to do with the 2. Do I want to have the 2 multiplied by the entire quantity? Or can we just kind of sneak the 2 back over inside? Can go either way with it. Maybe be really deliberate about it like that. Maybe call it C1. And so the final answer, we're going to multiply the 2 by this quantity, and we'll have something to the 6th power over 3 plus c, where c equals 2c sub 1, I guess. What goes inside the parentheses? There we go. So final answer, since the original integrand had x's in it, the final answer should have x's in it. So x squared minus 5x quantity to the 6th power over 3 plus the constant of integration. And check it with the quick derivative. Multiply the 6 by the 1/3, I guess, and you get 2 times the quantity x squared minus 5x raised to the 5th power times 2x minus 5. Take that 2 out in front and distribute it through the 2x minus 5, and you get the 4x minus 10. Sine cubed of 2x, I'm going to rewrite it as sine of 2x quantity to the 3rd times cosine of 2x dx. And the u is the inside function, sine of 2x. The derivative of that is not cosine of 2x, but it's 2 cosine 2x. But we saw how we could fix that a little while ago. Let u equal sine of 2x. Then du equals 2 cosine 2x. dx. Now, I need two things. I need the u, so that's no problem. This is going to be the u. But I also need a 2 cosine 2x. And it's a little bit trickier in this case than it was in the previous case, because there's not like I can just take, like there's a 2 in the way, and I can just drag it out in front. There's nothing there. I need a 2 there. So here's where I make out my Christmas wish list. Okay, what do I want? What do I need? Well, I need a 2 there in front of the cosine of 2x. So what do I do about that? Well, I could write a letter, well, email, text message, to Santa Claus, or I can just put a 2 there. Just like that. And so I will. I don't want to wait another, 22 days till Christmas? I'm just going to put a 2 there. Now, that's wrong of me to do that. I can't just put a 2 there unless I compensate for that somehow. So we can move freely in and out of the integrand by multiplying and dividing. So if I put a 2 on the inside, I can account for that by putting a 1/2 on the outside. And I can stay on Santa's nice list. All right. So I've got what I need. I've got the u right there. That's u. And now I've got du right there. So I can put the u where it goes. U equals sine of 2x. So that's a u cubed. And I can put the du where that goes. Du equals 2 cosine 2x dx. So that's du. So with that change of variables, that's a way nicer integrand. Instead of all of that, it's just u cubed du. No trouble finding an antiderivative for u cubed u to the 4th. So 1/2 u to the 4th over 4. Could decide whether to say 1/4 u to the 4th or u to the 4th over 4. So I'll go with u to the 4th over 4 plus c. C sub 1. So it looks like it's going to be, how to say this? The u was sine of 2x, so it's going to be sine to the 4th power of 2x over 8 plus c, where c equals 1/2 c1. Maybe put it down here.
Was that C necessary, that little last part of it?
It's not necessary if you do this. If you just say this is the integral of 1/2 u to the 3rd du, that might be what we're all more comfortable with. And if you leave the 1/2 on the inside and just say an antiderivative for that would be, let's see, 1/2 u to the 4th over 4, so that's 1/8 u to the 4th. So it's going to be 1/8 u to the 4th plus c. And so then you do the substitution and you get that. I just kept the 1/2 on the outside of the integrand, so I felt like I should probably do that. Because this constant of integration is technically different from this constant of integration, even though they're both arbitrary. I'm going to write this one as the integral of x to the 4th minus 16 to the 1/2 times x cubed dx. And it would appear that the inside function is x to the 4th minus 16. Now, although I skipped the step right there, we are taking the derivative. Du dx equals 4x cubed. And then writing in differential notation, du equals 4x cubed dx. There we go. Now I see the u right there, and I almost see the dx, see the du right there. Not quite. I don't want x cubed dx, I want 4x cubed dx. So I make it happen. I just put a 4 there. The integral of x to the 4th minus 16 to the 1/2. I need a 4, so I put a 4. I realize I'm not allowed to do that unless I account for that somehow, some way. So multiplying the integrand by 4, I can count for that by multiplying outside the integrand by 1/4. Now we look at it. You can see the u and you can see the du. So we put them in there, and then we ought to be able to integrate this. 1/4 times the integral of u to the 1/2 times du. There it is. That's du. If we add 1 to the exponent, we get 3/2. Dividing by that 3/2 is equivalent to multiplying by 2/3, so I think that's what I'd rather do. So it's going to be 1/4 of 2/3 u to the 3/2 plus c sub 1. So this is going to be 1/4. Actually, save a step there. 1/4 times 2/3 is going to be 1/6. 1/6 times x to the 4th minus 16 to the 3/2 plus c, where c equals 1/4 of whatever c sub 1 was. But it's arbitrary. So ultimately, the final answer, if I have a solutions manual, something like that I'm trying to build, I can put plus c there, and it really didn't matter what it is in reference to this other c sub 1, because we didn't know what c sub 1 was.
I'm lost on the 2/3.
2/3, well, it's u to the 1/2 will give us u to the 3/2 over 3/2. So we add 1 to the exponent and then divide by the new exponent that we got. And then multiply by the reciprocal of 3/2 to get the 2/3. So it looks like that. Now, I don't know what new the next example will have to offer. Maybe a little bit. Actually, 3a is going to feel like old hat, I think. 3b may have a little bit to offer. Let's look at 3b and see if we can make sense out of that. Definitely, yes. Take a break right after this. Let u equal, what does the inside function look like? Let u equal 6x to the, is that what you said? I'm sorry.
Is that right?
6x to the 4th? That's not what you said? It is right. I'm not sure if it's what you said or not. The inside function, what's the outside function going to be? Cosine. So we're composing cosine with 6x to the 4th, and this should work for us. Because what's the derivative of 6x to the 4th? 24x cubed. Never mind the 24. The important thing is the x cubed, because we have a factor of x cubed right there, and we really need the derivative to have a factor of x cubed. It does, and so we should be good. We should be able to get there from here. So du equals 24x cubed dx, and we can substitute what we need into the expression. This is the integral of, all right, I don't have a 24x cubed, so I put a 24 here. I put an x cubed dx there. I put a cosine of 6x to the 4th right there. And I put a 1/24 right there. My du is 24x cubed, dx. And that determines what I have to put into the integrand to make this thing work. So if it's going to happen for me, I've got to have a 24x cubed there. So I write it 24x cubed, 24 in red because there wasn't a 24 in the original integrand, and then just account for that. Now it should be noted, if I needed a 24x to the fourth, I'm out of luck. Because I'm not allowed to put a 24x on the inside and a 1 over 24x on the outside. That's illegal. I can't get by. Even Santa Claus will let me get by with that. Because I can't move x's inside and outside the integral. That's not allowed. But constants, yes, we can do that all day long. We can move constants in and out. So 24 on the inside, 1/24 on the outside, and we're good. So it's going to be 1/24 times the integral of the cosine of u du. Totally put me on his naughty list if I tried to put a 1 over 24x out in front of the integral there. So antiderivative for cosine u. Can we go with just plain old sine u in this case? So sine u plus c sub 1. So it's 1/24 sine of 6x to the fourth plus c, where the c I'm writing is equal to 1/24 c sub 1. Yes?
Isn't the derivative of the cosine the negative sign?
Well, derivative cosine is negative sign, but since it's reversed, if we were checking our answer right here, we'd take the derivative of sine. Yeah. Yeah, for antiderivatives, the sign flips the other direction. I do want to pause, though. When we do the substitution, it's vital that we get rid of all the x's. If we don't want to have an integral where u is a function of x is a function of u, they depend on each other somehow, some way, and we're left with a mixture of x's and u's. When we start out with an integrand with nothing but x's, and then after we do the u substitution, we want to be looking at that and not seeing any x's at all, just the variable u. So we can sort of try substitution here, but it doesn't initially look like it's going to make all the x's go away. I see an outside function, the square root. I see an inside function, x minus 2, so I could kind of get it started if I let u equal x minus 2. That begins the process. And that has a nice enough derivative, du dx equals 1. So actually, du equals dx. So where I see a dx, I don't even have to finagle a constant here. I just pick up the dx and put du in its place. And where I see the x minus 2, I pick up the x minus 2 and put u in its place. But I still have an x right there on top. And it looks like this. U in place of the x minus 2, because that's what u is. Du in place of the dx. What am I going to do about that x in the numerator?
Ask Santa Claus to remove it.
Yeah, I wish. Well, let's see. U equals x minus 2. So what's x?
Plus 2.
U plus 2. Almost as good as getting Santa Claus to remove the x. We can substitute u plus 2 for x and have this. The integral of 3 times the quantity u plus 2 over, I'm going to go ahead and write u to the 1/2 down there, du. Just like that. So sometimes if there's an extra factor of x that's kind of left there, if you can take this expression and solve it, it might not always easily solvable for x in terms of u. But if you can solve that for x in terms of u, you can use that expression with u's in it, u plus 2 in this case, and put it in for any extra x's that you were unable to get rid of with the direct substitution. So it worked fairly well in this case. Now we are left with this expression. Could be a little tricky to come up with antiderivative. Let's see. I think I want to leave the 3 pretty much where it is. Actually, I want to distribute the 3 across the parentheses and write 3u plus 6 over u to the 1/2. We just have a monomial in the denominator, and so I think this is workable if we write this as 2 separate fractions. Write it the integral of 3u over u to the 1/2 plus 6 over u to the 1/2. Because if we can do that, then we can use the power rule. The power rule for integration, for finding an antiderivative for each one of these terms. U to the 1 over u to the 1/2 is u to the 1/2. So this is the integral of 3u to the 1/2. And then if we have u to the 1/2 in the denominator, we need u to some power in the numerator. So I'm going to say u to the negative 1/2. Multiplying by u to the negative 1/2 is equivalent to dividing by u to the positive 1/2. To apply the power rule, it needs to be multiplied by u to a power instead of divided by u to a power. So now we can find antiderivatives, add one to the exponent, in each case divide by the new exponent that we get since they're fractions. Instead of dividing by those fractions, we can multiply by the reciprocals of those fractions. So integral sign goes away. So it's going to be, oh, is that 6? What is that? It's going to be 3u to the 3/2 times 2/3. Add one to the exponent. 1/2 plus 1 equals 3/2. And then divide by 3/2. That's equivalent to multiplying by 2/3. Okay. So it looks like that. And then add 1 to the exponent to get 1/2. And then we have to divide by 1/2. That's equivalent to multiplying by 2. So 2. And then plus c. So we're going to have 2 u to the 3/2 plus 12 u to the 1/2 plus c. That's going to be, I need the x's in the final answer. So x equals, no, u equals x minus 2. So it's going to be 2 times x minus 2 to the 1/2 plus 12 times x minus, sorry, I don't know where the 1/2 came from. 3/2. 3/2 plus 12 times x minus 2 to the 1/2 plus c. Now, as far as I'm concerned, that would be a really nice way to leave your final answer. The original expression had radicals rather than fractional exponents. So another alternative might be to convert this to radicals. X minus 2 to the 3/2. We're taking this square root, but then we're cubing it. It could be written maybe 2 times this, no, 2 times x minus 2 times the square root of x minus 2 plus 12 times the square root of x minus 2 plus c. I believe it would look like that if we tried to write it with radicals rather than fractional exponents. But I think it looks nice enough with the fractional exponents, so I'm going to leave it like that. All right.
Yeah, that's,
Q.
so is x minus 2 supposed to be cubed on there?
Well, this extra factor of x minus 2, basically you have 3 x minus 2s, like that. It is cubed. But I take 2 of them, these two,
Okay.
and I multiply those together to get that, x minus 2. That's where the extra factor of x minus 2 comes from. Definite integrals. Definite integrals using integration by substitution. You would think maybe we don't even need to talk about this, because if we can evaluate an integral by substitution, and then we want to evaluate a definite integral, it would seem that we should just evaluate the integral, just like we did, just like we've been doing this whole hour. And then, once we get the final answer, put in the upper limit, put in the lower limit, subtract, write the final answer. What more needs to be said? Well, a little bit more can be said because it makes things a little bit nicer. If we use a different variable, rather than going to the new variable and coming up with an antiderivative and then going back to the original variable and using the original limits of integration when we plug in those numbers at the end, what we do is we go to a new variable, u, or maybe in this case theta, and then we change the limits of integration based on the new variable. We go from x values to theta values. So rather than integrating from a to b, we look at that expression we used for the substitution, and we integrate from g of a to g of b. So what the advantage has is that we go to this new variable, and then we don't look back, because the answer is going to be a number, not an expression with x's in it. We don't have to go back to the x's. We just go to the new variable, and we stay in that new variable, and then we use that to come up with the final answer, and we write down the final answer, the number, and then we're done. So we don't have to go back to the old variable after we do the change of variables. That's the advantage of this substitution. So let's try this. I've got this one involving sines and cosines. Hopefully it's not too far over the top. I could have just thrown in one with u's, I suppose. But we want to integrate 6 sine squared theta, cosine theta, from pi over 6 to 3 pi over 2. And we want to do this using the substitution u equals sine theta. Well, when we do that, what I will say is the lower limit, u sub 1, is equal to the sine of pi over 6, which is equal to the sine of 30 degrees, which is 1/2. And the upper limit, u sub 2, is going to be the sine of the upper limit, 3 pi over 2. 3 pi over 2, all the way down at the bottom, 270 degrees, is -1. So what we do is, when we write this, we're going to use new limits. Let me see what the integral is going to look like. U equals sine theta, so du d theta equals cosine theta, so du equals cosine theta d theta. So there is du right there. That's du. And sine theta is u, so this looks like 6u squared du. Sine squared theta is u squared. Cosine theta d theta is du. So it looks like 6u squared du, but instead of going from theta equals pi over 6 to theta equals 3 pi over 2, we're going from u equals 1/2 to u equals -1. Now notice the upper limit is a lesser number than the lower limit, but that's okay. We'll just integrate this and put the upper limit in first, and then the lower limit, and then we'll subtract. And I believe since 6u squared is a non-negative function, for any value of u, it's not going to be negative. Going from 1/2 to -1 is going to give us a negative answer. But that's okay, because I believe if we were to look at this graph, more of it than not, would lie below the x-axis. So I think we can expect a negative answer. Need an antiderivative, no trouble here. 6u cubed over 3. And would that be 2u cubed? When we take the derivative of 2u cubed, do we get 6u squared? So 2u cubed is equal to an antiderivative of 6u squared. So we just need to substitute the -1 and substitute the 1/2 and subtract. So it's going to be 2 times -1 cubed minus 2 times 1/2 cubed. That's going to be -2 minus 1/4. I want to say -2 and 1/4. Have we not used the calculator yet today? I guess not. So if I graph y equals, clear that out, 6 sine x to the power of 2 times cosine x. Confirm that I am in radian mode and zoom trig. Yeah, between pi over 6 and 3 pi over 2, it looks like more of it than not is below the x-axis. So I'm thinking the net signed area is going to be negative. Second, calc 7 pi over 6, lower limit, and 3 pi over 2 for the upper limit, negative 2.25 is what we get there. But I think it's probably easier than putting the thetas back in and then integrating that antiderivative from pi over 6 to 3 pi over 6. It's equivalent to doing that.
Can we just give you the answer?
Well, I want to see some of that right there. There we go. Some of that. Maybe all of that. So what's going to be on the test? In case I forget to remind you, some more definite integrals there. In case I forget to remind you, be sure a week from today, when we were talking about what to expect on the final exam, that you bring all of the previous tests that you've taken in the class. So I can point out specific problems that are really, really important and specific problems that are not so important from the previous test. We'll look at all those. Hopefully I'll have your tests from this coming Wednesday graded, so I can give those back to you, and you'll have that as a reference. And then as far as studying for the final exam, it'll be whatever types of problems showed up on previous tests, plus whatever is in these last 3 sections that I want to mention. There's no way I can cover those in complete detail, but there are a couple or 3 important topics I want to make sure that you have a look at before the final exam. Now, let's look at the homework for which I at last have solutions, and let's see which of those problems are going to be key for you. Midpoint, left endpoint, right endpoint. Here's what I'd like you to do for a problem like that. So for this problem, the 2x squared minus 1, what I'm really looking for is this. If I say, okay, give the right endpoint approximation for the integral, I think it's probably best if on your calculator you just define y1 to equal, or I guess your calculator doesn't have the of x, y1 equals 2x squared minus 1. On your paper, you can let f of x be that 2x squared minus 1, and then basically you're just kind of pulling from memory the formula sigma. Let's say we're going to do the 50 rectangles. Sigma k equals 1 to 50, and basically you're evaluating the function at 50 different values of k as it works its way across that integral, and each time you're multiplying by the width of that little interval. So it's going to be b minus a, what's that, 6 minus 1 over 50. That's how wide each of those little rectangles is going to be, 6 minus 1 over 50. And then each time you have to evaluate the function. Well, how do you figure out, how does the calculator figure out what those values where it has to be evaluated at? Well, it's going to start at 1 plus 1 plus k times 6 minus 1 over 50. Since that's the width of the rectangle, if it's the right endpoint approximation, then the first one would be whatever 1 plus the length of the rectangle is. So when k equals 1, you scoot 1 width of the rectangle to the right. When k equals 2, you scoot 2 to the right. When k equals 3, you scoot 3 to the right. So what I want to see on your paper is this, and this, and then what you want to do is get your calculator to evaluate that. And it's just a matter of how to get your calculator to evaluate that. You can store 50 in the value of n using the STO button on the calculator. You can store the 50 in n, or you can just have your calculator just put a 50 there. Maybe that's the simplest thing. You can say sum of the sequence of the expression y1 of 1 plus k times, and let's see what, not k times. Yeah, k times, it actually is that. Times, what, 6 minus 1 over 50. Evaluate the function there. And then multiply by the 6 minus 1 over 50. And then a comma. The lower limit is 1. No, wait, the variable. The variable is k. The lower limit is 1, the upper limit is 50, and the increment is 1. You want to be able to get your calculator to evaluate that sigma notation. And that's the way to do it. I might ask for the right endpoint approximation. If I ask for the left endpoint approximation, then instead of being k, it would be what?
K plus 1 or minus 1?
K minus 1 for the left endpoint, and k minus 1/2 for the midpoint. K minus 1/2 for the midpoint. Now, if you have trouble with the y-vars, the vars button on the calculator, this one, where is it? Right, let's go red. Right there, you know, that's the button that you punch to get the y1 up. We don't use that one every day, but you go there with your second quit, clear, to get the y1 1. So you want to make sure that you can go there to get that for your y1 of. Now, if you
put it in your y equals first, right? And then
right.
y1.
Yes. Well, yeah, you put it in like your y1 equals, you just put in the 2x squared minus 1. You make sure that's stored in your calculator. And once that's stored, then you can go to the sum, second list of the sequence, and then you carry out the rest of it. Yeah, we went through that in class, but make sure you can get your calculator to produce that for you. Whatever function that I use there. Given a definite integral, we've seen most recently that these definite integrals can be evaluated by finding antiderivatives. With the exception of problem 4, we do not yet know how to find antiderivatives for these other two functions. So that's something that will be done in Calc 2, but we're not going to find antiderivatives for these expressions. But I would like you to be able to use a combination of the properties of definite integrals and little portions of circles, semicircles, quarters of circles, and formulas from geometry involving the area of the circle to evaluate expressions like this. So I would like you to be able to figure out what the graph of just plain old y equals, missed it, the graph of just plain old y equals this looks like. And if you can find the graph of that, then you can find a value of the integral from -4 to 1 of the square root of 25 minus x minus 1 quantity squared dx. You can multiply that by 4, and then you can add the integral of 6 dx, and then it won't be so bad. If you just try to graph this, I don't know what that is. And I don't know how to find its area either. But this one is a portion of a circle. It's either is it a fourth? Yeah, I think it's a fourth of a circle. So you can evaluate that using a formula from geometry, and evaluate the entire integral using that together with formulas. Right. Pi r squared. Pi r squared. In this case, 1/4 pi r squared, because it's 1/4 of a circle. Yes, I took geometry the fall after Star Wars Episode 5. It was after the introduction of Yoda. Anyway, my geometry teacher had a big Yoda poster in her room. That's why I remember that. Anyway, section 5.4. For this, I'd like you to find the antiderivative. Find the antiderivative, substitute the 5, substitute the -3. Get an answer. That should be an easy problem. 8, we did one of these right at the beginning of class. The one with the square root of cosine x in it. So I think of this as an easy problem. For f of 3, you put the 3 right there, and what do you get?
0.
You get 0. For f prime of 3, you first find f prime of x by taking the derivative of this and the derivative. Don't worry about that expression. By the fundamental theorem of calculus, all you have to do is put x's in there for the t's. And you have e to the x over x plus 1. And then you substitute substitute 3 for x. So it's e cubed over 3 plus 1. That's all there is for the b part. So you want to look at it, you want to think about it, but that's all that goes on. You substitute x's for t's, then you substitute 3's for x's.
That would be our answer for that?
That's the answer, e cubed over 4. And then for the third part, for the second derivative, you actually do have to use the quotient rule and find the derivative of e to the x over x plus 1. That involves the quotient rule. So recall the quotient rule from somewhere. 9, we did a problem, I think that was Calc 1, right? Number 9, the integral from 2 to x, we did a problem very much like that. I think we did that for sine. Problem 10, I think you can handle. Problem 11, I would love to put on the test, but I've not yet told you how to do it, so I would feel a little uncomfortable putting that on the test. It involves the chain rule. I'll put it on the final exam. So you put a star by that and say, this is going to be on the final exam because Mr. Mizell couldn't find a way to squeeze it on exam 6. Basically, you substitute tangent x for t there and for t there. So it's tangent squared x minus 3 tangent x. But we're actually composing this integral function with tangent x. So the chain rule says we have to multiply by the derivative of tangent x. So we have to multiply by secant squared x. It's not difficult, but I hate to make 8 points on the test, something we're spending fewer than 8 minutes on. So that's not good. In fact, is our time already up? It's 2:07. We have 3 more minutes, maybe, possibly. Find the total area between the curve and the x-axis. What if it's not positive on that entire interval? 12x cubed minus 96. I very much dislike that. Minus 96, zoom 6. Is it going to be positive between 0 and 3? No, it's got an x-intercept at 2. Window, negative 100 to positive 100 with the y-scale of 10. We ran into one like this, the one with the absolute value in it, absolute value of x squared minus 9 or something like that, I seem to recall. We want the total area bounded by the curve. The problem is some of the area is below the x-axis and some of the area is above the x-axis. So if we just use the fundamental theorem of calculus and find an antiderivative, plug in the 3, plug in the zeros, subtract, we'll get the difference between these two. But we don't want the difference between these two, we want the sum. So the key to this problem is breaking it apart and going from 0 to 2, figuring out what that area is. It'll be negative because it's below the x-axis, but you can just take the absolute value of that. And then going from 2 to 3, finding that area, writing that down, and then adding those together. So that's the thing. The total area, we've got to take this and that, figure out what they are individually, break it apart, and then that will do it. That will do it for you. We got to skip 12, 13, and 14. Wait. 13. Now 13 is actually good. We did a problem like that. We did a problem like that.
Last time.
Yeah. 14 we did not. So skip 14. Not 14. 13's okay though.
When did we do that problem?
13. Either last time or the time before last. Yeah. Look at 13. 14 is a great problem, but it's not going to happen for this test. 15 we did today. 16 and 17 we also did today. Toward the end, evaluating definite integrals. You would need to integrate by substitution. Probably you want to change the limits of integration for each of those. So I think 15, 16, and 17. Those look like section 5.5 problems. 15 and 16 and 17 do? What about 5.5? I know my time's up. Let's see what else I can scratch. Everything. So this one you would need to use polynomial division and then attack it. This one involves a natural logarithm. I just don't think we've hit enough examples of those. It's a great problem. This one seems too extreme. This one you need to write it as sine x over cosine x, but we really ought to do that in class. I don't know about that one. Which, 30? Now 30 actually looks pretty good. Just let u equal sine x, and it's nice. It's really nice. That's maybe the nicest one on there. All right.